Now that we've gone through a brief introduction about when and why quantum mechanics is necessary, we want to get into starting to use it in a productive way, in a scientific way, and we'll be doing that over the next couple of chapters. Chapter 3 gives us an introduction of how to do that by asserting 5 of the 6 main postulates of quantum mechanics. There are 6 main postulates that summarize the basic concepts of quantum mechanics and the rules for how information is obtained from quantum mechanical calculations. We're going to look at 5 of those postulates here in Chapter 3. The 6th one we want to save until we introduce a little bit more material about the behavior of electrons. The 6th one is actually the Pauli exclusion principle, so we'll look at that one in a few weeks. But to begin right now, and we'll define these, and these will be important definitions for you to remember. That's a hint for preparing for the next test. The first postulate states that the state of a quantum mechanical particle is completely described, completely specified by a wave function that we'll usually denote with the Greek letter psi. The probability that a particle will be found at some specific time in a particular interval of space that's centered around a specific position is given by squaring that wave function at that particular time and position. And remember, we said squaring a wave function that may have imaginary components means not just multiplying by itself, but multiplying it by its complex conjugate. The conditions that are placed on postulate 1, in order for it to be true, the wave function has to be a single valued function of the spatial coordinates. The second derivative of the wave function has to exist and be well behaved. That means that the wave function and the first derivative of the function have to be continuous functions. So those points that are underlined here on the slide are the main points of description about the wave function in order for it to satisfy postulate number 1. Additionally, the wave function has to be normalizable, and it can't have any place along the interval we're considering where it has an infinite amplitude. Postulate number 2 of quantum mechanics states that for every measurable property of any classical mechanical system, such as position, momentum, energy, angular momentum, we'll list several in future chapters of the course, but there is in existence a corresponding quantum mechanical operator that can be used to calculate that property on a quantum mechanical system. Any experiment in the laboratory has to measure a value for such an observable that is simulated in theory by operating with that operator on the wave function of the system. Now we'll talk a little bit about what we mean by operators. All quantum mechanical operators are Hermitian. That means that they have eigenvalues that are real. Mathematically, we can state that this way, that if we operate on a wave function and then multiply that operation by the complex conjugate of the wave function, we get the same thing that we would by multiplying the original wave function by the complex conjugate of the operator on the original wave function. That's a mathematical way of restating this assertion about quantum mechanical operators right here. Operators always operate on from the left on the wave function to their right. That's an argument of semantics. That's the language of mathematics. When we write an operator, it is operating, whatever mathematical instructions are in here, it is operating on the function we've written down to the right of it. An order of operation is important with operators. If we have operator A and B operating on a wave function, that may be different than operator B and then A operating on that same wave function. And we'll talk about why that's important in a little while. Postulate number 3 states that in any single measurement of the observable that corresponds to a specific operator, the only values that can ever be measured for that particular observable are the eigenvalues of that operator. This is true even if the wave function is not an eigenfunction of the operator. Now think about what that means. It sounds like we've contradicted ourselves. The only values we can measure for any observable are eigenvalues of that operator, even if the function isn't an eigenfunction. You'll say, well, if the function is not an eigenfunction, there are no eigenvalues. We can't measure something. That's not completely true. Let's think about how that can be the case. We said earlier that any wave function, whether it's an eigenfunction or not, can be written as the sum of eigenfunctions for any particular operator. And so if we are measuring an observable on a particular system that's described by a function that's not an eigenfunction of the operator, our measurement will return one of the eigenvalues that is appropriate for the eigenfunctions that make up that sum. And that leads us to one of the concepts in our next postulate. Postulate number 4 states that if the system is in a state described by a particular wave function, and the value of an observable A is measured once on many identically prepared systems, the average value of all of these measurements is given by what we're going to call expectation value or average value. That's this notation right here. And that's given by this expression here. Look at what we've got. Operator operating on the original function, that multiplied by complex conjugate, integrated over all space, divided by the square of the function, integrated over all space. Now remember, this will be 1 if we've normalized the function. And so the expectation value for a particular observable is this, where the observable we've denoted with a specific lowercase letter, the operator with that same capital letter, and we will generate the expectation value of a measurement by performing this mathematical operation. That is postulate number 4. The proof that postulate number 4 is true for the case where the function is an eigenfunction is trivial, and I can show that on the board next class if you'd like me to. But when the function is not an eigenfunction, it can be expanded into a complete set of functions that are eigenfunctions of A. And so we'll get a wave function that looks like this, where each of these phis or phi, depending on how you like to pronounce your Greek letters, represents an eigenfunction that when placed in an appropriate sum add up to the original wave function. We can generate the expectation value then by integrating that operator having operated on the sum times the complex conjugate of the sum. Now think about that for a moment. Take a look at that. Pause the video if you have to, and then we'll move on and finish this proof on the next slide. Again, here's that. If we take that expression, if we operate to the right, what we're going to get is that operator on each of these wave functions is going to return that wave function times the eigenvalue that is appropriate for that wave function. Then we're going to take this whole sum and multiply it by this whole sum. That's going to get us a lot of foiling. We're going to generate a large number of ideals there, but what it's going to work out to be is a sum of the normalization constants squared. I'm sorry, the sum of the normalization constants multiplied by one another times the eigenvalue that was generated here for each particular wave function, and then all of that times uh, the one wave function multiplied by another. But remember, we said if we integrate that one wave function multiplied by another, we get 0 in cases where they're not the same wave function, where m and n are different. So anywhere where m and n are different, that term is going to drop out. And so only terms that survive the foiling are going to be places where this is a particular wave function and this is that same wave function's complex conjugate. So the expectation value is the sum of the squares of the absolute value squares of the normalization constants times the eigenvalues. And since those normalization constants squared will relate to how much of the original total wave function is made up by that eigenfunction, the sum of all of those squared makes is 1. And so what we're doing is we're finding out that what we've calculated by performing this operation is not just an average value for A, but a weighted average value for A, where each eigenvalue is given an importance that's related to the square of the constant for that eigenfunction. Alright, so this is in contrast to what we expect in classical mechanics. The value cannot be predicted for any one particular measurement, but we can calculate a probability for the most likely value of each measurement in a case where our eigenfunction is not, in a case where our wave function is not an eigenfunction of the operator. The expectation value calculation gives us a most likely value for any one measurement of the observable, but without predicting the value of any one particular measurement. Now the question is, what happens to the wave function and the expectation value after one measurement corresponding to postulate number 4? And the answer to that question comes from postulate 5. Postulate 5 says that the evolution in time of a quantum mechanical system is governed by the time-dependent Schrodinger equation. The idea here is that if we make a measurement at any particular time, postulate number 4 applies. We've got an expectation value with probabilities. But if we want to know what the system will look like at some time later, postulate 5 applies. We have determined the system at a specific time with our first measurement. Once we make a measurement, the original wave function that was a sum of eigenfunctions is no longer that sum. It is the eigenfunction that corresponds to the eigenvalue we measured. Each measurement has to return an eigenvalue. The measurement itself determines the system, collapses the wave function down to one function from the sum. That is something that Einstein had a big problem with in quantum mechanics. The system is determined by measurement. And for the rest of time, if we measure that same system again, the system only behaves under that one function, not under the sum. Einstein didn't like a system that was dependent on being measured, but he could never, though he tried and tried, prove the opposite.